Okay, let's take a look at a couple of examples. It says find the Taylor series for this function centered at 0. In other words, we're looking for the Maclaurin series. So we know the Taylor series is centered about A is given it like this, but we're looking for the Maclaurin series, which means A is just 0. So we're going to replace our A's with 0. So ultimately, I'm trying to find my coefficient Ci, and in taking derivatives, I want to find a pattern for this, and looking with this function right here, and then plug it in and see what happens. So I'm looking for the first derivative of f of x, which is just 2 to the x times ln of whatever is there, so ln of 2. And then I have second derivative is just going to be again 2 to the x, and this guy that I had times ln of the base, which is another ln of 2. If I want to go look at the third derivative, you see what's happening. The derivative of 2 to the x is just 2 to the x ln of 2, and then these two guys are still waiting there. So you notice a pattern already that at the first derivative I have 1 ln of 2, at the second derivative I have 2 ln of 2s, at the third derivative I have 3 of them, at the fourth derivative I will have 4 of them. I'll do one more. So again, the only term you're differentiating is 2 to the x, which is just going to go to 2 to the x ln of the base, ln of 2, and then these 3 guys are still waiting. So if I were to write a pattern for this, at the fourth derivative I have 2 to the x and then 4 of these guys stacking up. At the third derivative I have 3 of them stacking up, at the second derivative 2 of them, at the first derivative just 1 of them. And if you want to include this guy, you can think of that as ln of 2 to the 0, because ln of 2 to the 0 is just 1 anyway. So at the 0th step I was there, first derivative, second derivative n is 2, third derivative n is 3, fourth derivative n is 4, and even without plugging in anything, I can see that the pattern, when I get to the nth derivative, when n is equal to n, is just going to be this 2 to the x that keeps appearing times ln of 2, but stacking up n of them. So I could go put in, remember our center is 0, I could go put in 0 here, and we'll end up with 2 to the 0, ln of 2 to the 0, which is 1. I could put it here, the center is 0, 2 to the 0, ln of 2 to the 1, which is just ln of 2. I could put it individually again here. When x is equal to 0, I have 2 to the 0, ln of 2 to the 2, which is just ln of 2 to the 2. I could put it for each one, or might as well just put it in the general one I found. When x is equal to 0, or the center is 0, I have 2 to the 0, ln of 2 to the n, and 2 to the 0 is just 1. So basically I found that the nth derivative at 0, when I plugged in 0, is simply ln of 2 to the n. So the pattern after differentiating and trying to get to the nth derivative evaluated at 0, I ended up with ln of 2 raised to the 0, everybody else went away. So I basically now have the item I'm going to go plug in there. So instead of the highlighted piece, I'm just going to put ln of 2 to the n. The n factorial was already there, x to the n, and I'm pretty much done. My exponential function 2 to the x, centered at 0, has these Cn, or these coefficients, for x to the n. So I got the Taylor series representation for it. That was part A. I was able to figure out a pattern for the nth derivative at 0. Find the radius of convergence. Well, for that, I could just do maybe a ratio or a root test. I have factorials involved, so maybe I'll just go ahead and do a ratio test. So for the ratio test, I'm going to look at the limit as n goes to infinity. These are, remember, my a sub n, my coefficients. So ln of 2 to the n plus 1, x to the n plus 1, all over n plus 1 factorial, times, let's take the reciprocal of a sub n, so I have ln of 2 to the n, and n factorial, nope, I did that wrong, it's x to the n. So let's do some cancellation. So once I expand this n plus 1 factorial, these guys are gone. Once I open these up with their exponents, ln of 2 to the n is gone, and x to the n is gone. So what I have left over, it looks like, in the numerator are these guys, and in the denominator, this is the only guy left over. So we're going to end up with limit. As n goes to infinity, these two are independent of n. I'll pull them outside, and inside I have a 1 over n plus 1. And as n goes to infinity, it looks like this guy goes to 0. So I end up with 0 times this business I pulled out, which is 0. And this is always less than 1. So by the ratio test, we just showed that the radius of convergence for this power series is infinity, which means 2 to the x is captured by this power series from negative infinity to infinity as I open this up and as n goes to infinity. We also had a part C. So we found part A by doing pattern analysis, basically. We found part B, finding the radius of convergence. And part C says give the third degree Taylor polynomial approximation for f of x about 0. So once I have the power series, all I need to do is open this up and go up to the third degree polynomial that captures this function well about 0. So basically, before we were calling in partial sums and looking at partial sums, let me copy this down. Okay, so I have this as my power series. I'm going to let n equal to 0, 1, 2, and 3, and spit out the terms. When n is 0, that's a constant. 0 factorial is just 1. X to the 0 is just 1. I get 1. Plus when n is 1, I get ln of 2 to the 1, x to the 1, and 1 factorial is just 1 anyway. Plus when I put in 2, I get ln of 2 squared over 2 factorial, which is just 2, x squared. Plus when n is 3, I get ln of 2 cubed, x cubed, over 6 factorial, which is, or I'm sorry, 3 factorial, which is 3 times 2, which is 6. And all I needed to do was go up to the third degree Taylor polynomial. So this polynomial captures 2 to the x pretty good around 0 for the radius of convergence being big. If I go all the way ends, and theoretically this, if I go all the way up, this will capture 2 to the x all over the place. But all we needed for part C was a third degree polynomial, so that's good enough. We're done with part C as well.